Hello everybody, in today's video we'll be walking through how to implement a feedforward neural network using TensorFlow and Keras. We'll also dive into the key concept of backpropagation, which powers learning in deep learning libraries. Since we talk about learning, we already know that in neural networks we use gradient-based learning to find the optimal parameters or weights. And these parameters correspond to weights that we have in neural networks and also the bias terms that we discussed in the previous lecture. And the main idea behind gradient-based learning using stochastic gradient descent is that at each iteration, so we have an iterative process, we have the current parameter vector at iteration t, and we want to find the next best solution, right? So you want to go from theta t to theta t plus 1, and we do this using the gradient information. This is the notation for the gradient of the loss function at the current solution, and I use this gt to represent this gradient of the loss function at time t. The other important aspect of a stochastic gradient descent is the learning rate, or a step size, which shows how far we move in each step, right? So this gradient shows us the direction, and then this eta is the step size or the learning rate that shows us like how much we want to go to the opposite direction of the gradient, because also we do have this negative sign here. One of the important things that we have to recall from one of the earlier lectures is the idea of momentum. So the issue is that with this, the original update formula that we have here, that the update that we have at each iteration depends on the gradient at that time. And if for some reason we are at a local minima or some other situations like that, we are going to get stuck at a suboptimal solution. And therefore, the goal is to always be able to get around these problems and be able to get out of these local minimas. And one of the ways we can do this is using this idea of momentum, where we introduce a velocity or inertia term, which we showed that using VT, that keeps track of the historical gradients or previous gradients. And this helps us to have a direction that we can move towards that, even though we get to some flat or noisy regions. And the idea is very similar. So the update formula is this theta t plus 1 is assigned as theta t minus the learning rate times now the velocity. And this velocity is like related to the previous iteration or the previous velocity by this parameter beta, which should be less than 1, and the current gradient, right? So we have both information about the current gradient and the previous gradients that are encoded inside this VT or velocity term. And once we update VT plus 1, we substituted in the second equation that we have here to update model parameters. Something I'd like to very quickly discuss here is that this type of updates that we have here acts like an exponentially weighted moving average. So what this means is that let's simplify a little bit this first equation that we have for the velocity and see what this means in terms of the gradients from some other previous iterations. So what we do, we're going to start with what we have here, but then we know that v at time t can be written as beta times v in the previous iteration, which would be vt minus 1 plus gt minus 1, right? So that's how we get this part here inside parentheses. And so now we can see that we get beta squared vt minus 1, beta gt minus 1, and then the current gradient. So you can see that velocity term here in summary is keeping track of the previous gradients, but we have this sort of like, weighted moving average where we have beta and then we have beta squared. And if we plug in here vt minus 1 according to vt minus 2 and gt minus 2, we go one step back in time. And this is like what you can, for example, like see here, right? If we go one more step. And the nice thing is that if we assume right, that each of these terms that we have here, these gradients, are bounded. And we want to make sure that we don't run into issues with like exploding gradients or something like that. Then we can just see these 1 plus beta squared plus beta cube, etc. If we just add all these terms, as long as beta is less than 1, this can be written as the sum from 0 to infinity of beta raised to the power of I. And this is something that you probably have seen in calculus. So the result of this summation is 1 over 1 minus beta, meaning that it's actually finite and even have a closed form solution. So therefore, this is a good sign that we can use momentum to be able to get out of noisy or flat regions when we are solving this optimization problem. And at the same time, this is a well-defined problem. As long as these gradients are bounded, we can show that we always have a bounded velocity term, right? Because that's kind of like what it appears in our upper bound. And this takes us to the idea of backpropagation, right? So the main thing that we need to do, as you just saw in this equation that we have here, is to find the gradient at each iteration, the gradient of the loss function. And so the way that we can find these is using this idea of backpropagation, which allows us to flow information backward in the network, meaning that now in order to find the gradient, we can always start from the end of the network where we have the loss function and then find all partial derivatives and gradients. And the key idea here is using the chain rule of calculus, which we can use to compute derivatives of functions that are in the form of composite or nested functions. Before explaining this part, let's go through a very simplified example where we are importing TensorFlow as TF. So right now we want to move towards neural networks and deep learning. That's why we are starting to work with TensorFlow instead of like scikit-learn. And in order to explain you what's happening here, it's easier first to visualize this. So you can see that, let's say we have a very simple model where we have two inputs, X and Y. So think of these as the first layer of your neural network. And then let's say in the next layer, we have two neurons, U and V. And here is the sort of like the equations that we have. So U is 2 times X, meaning that it's only connected to X. It's not connected to Y. There's no connection here. And V is equal to X plus Y, right? So, so there you can draw these connections with the weights or strengths of these connections written on them, right? 2, 1, 1. And then we have also the final sort of like layer here where we find a weighted sum of U and V. So it's 3U plus 5V. So if I ask you to solve this, by hand, so you're going to say that, well, I want to find the partial derivative of f with respect to x. And it's very easy to kind of like visualize this because we have two paths to get to x from f, right? So one is to find the partial derivative of f with respect to u, and then partial derivative of u with respect to x. That's exactly what we have here. But then we also have to add partial derivative of f with respect to v and v with respect to x, right? That's the basic idea of chain rule. And these are, each of these partial derivatives are determined by these strengths or weights that we have on these connections or edges. And we can do the math and you can see that the result is 11 for this partial derivative. We can do the same thing for partial derivative of f with respect to y. You can see that we can find partial derivative of f with respect to v and then v with respect to y. And in this case, we just have to multiply 5 by 1, right? So the nice thing here is that there's no path from u to y. Otherwise, we had to include that too. So that's how we would solve this problem by hand. And we're going to see that using the backpropagation, we can actually, find these partial derivatives automatically using automatic differentiation without even, again, like doing this by hand. So we can just define the forward pass, and by forward pass meaning that we can just say that u is equal to 2 times x. This is the equation for v, and this is the equation for f. And these libraries are smart enough to be able to backpropagate, right? So go backwards and find all these partial derivatives regardless of the size of the network. So this is exactly what we have here, right? So we have a function f, which is a function of u and v. That's exactly the equation we have. We have to define x and y. Here we assume x equals 2, y equals 3. We use gradient tape from TensorFlow. This is what we use to compute gradients using backpropagation. And inside here, we want to say that, well, we want to, at some point, find the derivatives or partial derivatives with respect to x and y. So that's why we use tape.watch. And then we define the forward pass for the first layer. And then the last part is finding this f. And now if we want to find these partial derivatives, we just have to say tape.gradient result with respect to x and result with respect to y. And if we run this cell, you can see that we got exactly the same result as before, 11 and 5, right? So that's, you can see, without doing this calculation by hand, we can find these partial derivatives. And that's exactly the same idea if we have a neural network model, right? So in this case, let's simplify things and say that we only have one input and we have one unit or neuron in each layer. So we use the same type of indexing here. We use the superscript to say that this is the unit in the first layer or first hidden layer. This is the second one, and this is the third layer, which is our output layer. This j is here our loss function, right? So let's say this is a regression problem, so we are using quadratic loss. So it's very easy to find the partial derivative of j with respect to a3, right? Because we know that this is just this nice quadratic function, so it's 2 times a3 minus y. But then if you want to find the partial derivative of the loss function, let's say with respect to w3, because we want to know how to update this, then we can start from the very end of the network and find the partial derivative of the loss function with respect to a3, and then a3 with respect to z3. We don't really show here z3, but the way that this works, remember, each neuron performs two operations, a linear combination and then the nonlinear activation function. So here I use a for after applying the nonlinear activation function, and z refers to what we have before applying the activation function. In other words, if I want to put this in terms of the logistic function that we used before, even in logistic regression, z corresponds to the logits, meaning what we had before, like the sigmoid or logistic function, and a here refers to what we have afterwards. But just to kind of like emphasize here, when we talk about neural networks, we don't have to just use logistic function. So this can be any nonlinear function, but this is a good analogy that we can use. And so given that if we call that activation function g, now we can see that now we have this derivative of the function g calculated at point z3, and then the partial derivative of z3 with respect to w3, right? And that's something that is what we have here multiplied by w3, which is a2, right? Because remember, what we have before applying the activation function is simply finding this weighted sum, which is a2 times w3. And if you want to find partial derivative with respect to w3, that's just a2. But the nice thing is that we can continue this journey towards the beginning of the network even one more step, right? So if you want to find the partial derivative of the loss function with respect to W2, now we already found the case that we have this partial derivative with respect to this part of the network, and now we have to go one step backwards. And the nice thing is that you can use some of these results that you already have. So you really recycle a lot of these partial derivatives and you don't have to find them from scratch, right? So whatever you want to do, whether you want to find partial derivative of j with respect to w3 or w2, you need to first find the partial derivative with respect to a3, and then you go one step backwards, right? So you can see here we have a3, and then we have z3, a2, z2, and then w2, right? So that's how we get to here. And if you want to do this with respect to W1, we have to go even one more step backwards, right? So I'm not gonna repeat all of these things here, but you can see that we go one step back to W3, and then to A2, and then to A1, And then from A1, so this is like really the main part that we added here. We go what we had before the activation function and then W1. And so in this case, you can see that we can find all these partial derivatives just by defining the forward pass without the need to solve this problem by hand. And this is the idea behind backpropagation and automatic differentiation, like this gradient tape that you can see here in TensorFlow, and there are alternatives in other deep learning libraries too, that they give us this valuable information that we can use to solve optimization problems. So this was just to give a quick idea of how gradient-based learning works in the background for training neural networks. But now let's use what we know to implement these feedforward networks or multi-layer perceptrons using TensorFlow and Keras. So what is Keras? So Keras is a high-level deep learning library built on top of TensorFlow that allows you to use simpler functions to build some neural networks very quickly. So if we really care about functionality and being able to implement everything from scratch, if just in case if you want to do a lot of customization, then obviously TensorFlow is a better option. But Keras in general is a high-level library that gives you still a lot of functionality without going into details very much, right? So the main difference is just like how you want to define these networks and how much time you want to spend. And since in this course we mainly talk about the basics of neural network training and implementation, we use Keras, but you can see that since Keras is built on top of TensorFlow, we still need to use some functionality from TensorFlow as well, but they're very much compatible. And the best way really to understand and learn and use Keras is to go through the documentation page. And this is the link that we have here. So I'm going to click on this, and you can see that in this case, you can go either look at some of the examples or go through the API, application programming interface. So you can see that if you want to define a model, there are a couple of options here. The main one that we're going to talk about today is the sequential class, where you sequentially put layers, and where are the layers in the layers API. So you can see that we have all sorts of layers here. And there are also more advanced things that you can use. And also we have optimization techniques, that are available here. Stochastic gradient descent, RMS prop is another version of a stochastic gradient descent where we have these ideas of momentum, and a few other things. And then we have also ADAM, which stands for adaptive moment estimation. So you can see that there are really like a lot of interesting options here, and as well as loss functions that we need to use to be able to complete the training process. So in this case, let's start really so like this step by step. So we're gonna import NumPy as NP, import pandas as PD. So these are things that we always import to be able to work with arrays and data frames, and also matplotlib for visualization. But the part that is kind of like new to this lecture is that we're gonna import TensorFlow as TF, and from TensorFlow we import Keras, right? Remember, Keras is a part of TensorFlow. And it's always a good idea to print the version of TensorFlow that you have, because these things get updated very frequently. The version that I have right now is 2.50. So as long as you have a version that is this one or newer than this, it should be totally fine. And let's create a data set that looks like very much like that exclusive OR or XOR problem that we solved by hand before. So in this case, in order to do that, what I'm going to do, I'm going to use these make blobs from scikit-learn datasets. Whereas the name suggests, we are going to have these blobs or clusters around some centers, right? So I'm going to have this 0 and 0, 0 and 1, 1 and 0, and 1 and 1. That's exactly where we had those 4 data points when we have exclusive OR problem. But I want to make sure that I add more data points, because now I want to really use a deep learning library rather than solving this by hand, right? So if I run this cell, you can see that what we have done here, right? So we have these 4 centers, we have these clusters. So we use make blobs to create these. The only thing also I've changed here to make sure that this is a binary classification, meaning that the ones at 0 and 1 and 1 and 0, they belong to the same class. So now we need to have like a decision boundary that looks like this. And then at the same time, we have these two other classes that are here. All right. So we cannot solve this problem using a linear classifier because there's no way we can draw a line to correctly separate these two classes where each class has two subclusters, right? That's what the challenge is here. Okay, so here we define the data, so X and Y. So this is all the input features, and we have two-dimensional data, and Y is the labels that we have that we get either 0 or 1. So it's a binary classification problem. So now the main part. So in order to define the model, as we said, we are going to use the sequential class. And since it's object-oriented programming, we are going to instantiate this class sequential by, running this cell and saying that this model is now a sequential model defined inside Keras. The next thing that we have to do is to add the layers, right? So it's exactly like, like putting, like it's very modular, like putting different pieces together. So once you want to define a layer, in the simplest case, you have to use the dense layer, right? So dense layer is exactly what we had before, right? It's a layer with some units or neurons in it, and it gets connected to the previous layer. If you want to know exactly how this works, so one thing that we can do here, so we can go to the layers API. So you can see that here it explains, some of these layers that are already implemented in Keras. And if you really want to know how this works, so it's the best way is to look at the documentation page, right? So you can see that there are all these options here that you can define. And one of the most important things here is units, right? So units is a positive integer which defines the number of units or neurons in that layer. There are also other options too, like what kind of activation function we want to use. Do you want to use a linear activation function, which is by default is just this identity function? Or do we want to use Sigmoid activation function? Do we want to define how to initialize the weights for that layer when we want to instantiate the model? And some other options, right? But the most important things are these two first options, right? Units and activation. You definitely need to pay attention to these two. And then the other thing is that whenever you want to add the first layer of the network or first hidden layer in this case, it's always good to define the input dimension, meaning that what do we expect to provide as inputs to this model, right? So in this case, we are saying that, well, we have two-dimensional inputs, meaning that in the first layer, we need to have two neurons. And then in the first hidden layer, we also want to have two units. So we're trying to do exactly the same architecture we had for that exclusive or problem that we had. And then finally, because in this case, we want to predict one label, which is the class label, we add one more layer for the output layer. And in this case, we only place one neuron. And it is important in this case to use the sigmoid or logistic activation function so that the network actually provides a probability score, right? And we use this because it's a binary classification problem. So once you define your model, add all the layers, now you have to compile it. And this is where you define your optimization technique. In this case, we are using SGD or stochastic gradient descent. You must define the learning rate. That's very important, right? That can really change the result of your model. We can put this 0.1, but later, as you will see, if we see like issues with divergence and things, not working, we can always try to reduce these. And then the loss function, we use the binary cross entropy. We covered this during the logistic regression lecture. That's why it was kind of important to talk about this then. And then let's just run this model.summary, which is very helpful because it tells us a lot about the number of parameters and everything else that we have, right? So in this case, for the first, remember the first layer, we have two elements, and then we have two units. So if we do the multiplication, we should have 4 connections. But remember also we have bias terms, right? So for each neuron, we have one bias term. So we have 4 plus 2, which gives us 6. So we have a total of 6 parameters for the going from the input layer to the hidden layer. And then going from hidden layer to the output layer, now we have 2 units in the hidden layer, 1 neuron in the last layer, which again gives us 2 times 1, which is 2, but we shouldn't forget about the bias term, and that's going to be 2 plus 1, which is 3. So you can see that in this very, very simplified case, we have 9 parameters that we have to learn, right? And in some cases, you can have non-trainable parameters, parameters that are fixed and we don't want to learn, but that's more kind of like, something more advanced architectures. And right now, everything is trainable. The nice thing is that you can actually right now look at this model.layers and see what's inside these layers and use this get underscore weights method. So you can see that already we have a 2 by 2 matrix, right, for the weight matrix, and a bias vector, which is 0 and 0. And if you're wondering why we have some numbers, because as you know, we know when you use gradient descent, you have to have some initial solution, which are usually random numbers. So in this case, you have these 2 by 2 kind of like metrics, which is the weight matrix. You need to go from the input layer to the hidden layer. And similarly, you can do this going from the hidden layer to the output layer. So you can see that this is size of 2 by 1, and then we have only one bias term. And if for some reason you have like here, for example, say I want to know the third layer, right? Because indexing starts from 0, then you get this out of range error, right? Because we only have 2 layers. And you can see this here too. We only have 2 model.add, right? So we have 2 layers, index 0 and 1, and there's nothing here. And in general, if we just say model.layers, you can see that. So we have these 2 layers. It's kind of hard to see right now because this refers to the memory address that where these layers are stored and then what's inside them. But if you want to know what's inside them, you need to use get underscore weights. And then the final stage, once you define your model and compile it, is to do training, and that's model.fit. And this is the part that you're using some gradient-based learning, a stochastic gradient descent in this case. And you have to set the number of epochs, meaning that how many times you want to go through the data, because we are using like batch-based updates, right? So in this case, we set batch size to be 8, meaning that each update only samples 8 data points at a time. And we go through the entire data in one epoch and how many epochs we want to repeat this. So if I run this, you see this really important information where you see the value of the loss function at each epoch. We know that, for loss function, it's always to get closer and closer to 0. And it seems that this is happening to some degree, but we are getting kind of stuck at 0.69. And in this case, since it's a classification problem, you can also look at accuracy, and you can see that the accuracy that we have is 0.69 and then 0.40. So it's kind of like going a little bit higher and then going down below 0.5. And this is not really good, right? Because it's a binary classification problem, meaning that if we just, toss or flip a coin, then you should be able to get close to 50%, right? So anything under 50% is really not ideal in this case. But it seems that the training is done, and after 50 epochs where we set, this is the value of the loss function, and this is our accuracy. The nice thing is that here, when I did model.fit, I assigned this to this history object, and inside this history, there is this history, and then depending on what you call this, for example, here, since we have a classification problem, you can look at the accuracy scores and the loss scores. So one way is to just look at this data that's been printed here, but it's nicer if we can visualize this. And you can do this using plot history.history and then defining what you're trying to plot, here accuracy, here loss. And we can plot this as the function of number of epochs. And you can see that, in terms of the values of loss function, we had a little bit of decrease, but we kind of got stuck around like 0.68, 69. And the accuracy is kind of like around 0.5, which is not really ideal. So this is a summary of what we saw printed before. And if you really want, at this point, you can also look at the updated weights. So we had the weights that we had before initially, and now after training, you can see that these are the updated ones. Something you can do, because it's a binary classification in a 2-dimensional space. In lecture 7 or week 7, we talk about plotting decision boundaries. where we create a two-dimensional grid using np.meshGrid, and then we create these sort of like, vector of all inputs, meaning that all the 2D coordinates that we have. And since we define the model, we can use model.predict, where we provide this input and then we look at the probabilities that we have, right? That's a nice thing about using Sigmoid or logistic function. And we can pass these probabilities to the contour plot. And we know that the contour plot gives us all the points with the same values, right? So this will give us a really nice picture about how our classifier is performing. So if you run this cell, this is exactly what we have here, right? So we have these, two classes, these two subclusters, they belong to the same class, and these ones. And these colors that you can see here are probability scores, right? So it tells us, like, for example, here, especially given that this is like more yellowish, that these data points that are here, so that's kind of like, if we have a test data point here, that's very likely to belong to this like yellow class, which is a really good thing. But obviously, we are making a lot of mistake because if we have a data point here in this top left corner, then you can see that it's more purple, which means that belongs to the wrong class, right? Instead of belonging to the yellow class. So that's why, decision boundaries and creating these 2D grids, if you have a two-dimensional classification problem, is very helpful because you really see why we get a really bad performance, which is 50%, because in some sense, we are dividing this entire space diagonally into two parts, and everything on one side is belong to one class, and then the other part to the other class, and that's not the right way to divide this data set into two classes. Something I want to mention is that now we're going to go talk a little bit about more advanced stuff after talking about the basics of defining neural networks and training them. Is that do we have to use the sigmoid activation function in the last layer? So the answer is no, and the reason is that these deep learning libraries are very smart and designed in a very nice way, in the sense that they know that in a binary classification case, you use the logistic function, and we already know that we don't really have to define this manually because this automatic differentiation can easily take into consideration that what kind of loss function we should use. And therefore, for the binary cross entropy that we used before, in this case, it was in where we defined model.compile. You can see that before we just say binary cross entropy, which means that we have to use the sigmoid or logistic activation function. But if we look at the documentation page, which I have here too, there is an option to set this from logits equals to true. And in this case, we directly work with logits. So remember in the backpropagation, I talk about this Z versus A, what we have after applying logistic function and what we have before, and that's what we call the logits. And so in this case, it means that we do not have to apply the sigmoid activation function. So this is kind of like a new version of what we had before. But for the last layer, when we have these units equal 1, we are not anymore using sigmoid, but instead, when we define the loss function, we have to make sure that we set from logits equals true, right? So this is telling us that we are going to work with logits, and please apply the sigmoid or logistic activation function yourself, and we are not going to add that directly here. And everything else is the same except one more important difference here. And instead of using the ReLU or rectified linear unit, in this case, we are using the exponential linear unit. And let's see whether this really makes a difference or not, because not using sigmoid function is exactly the same because we are using the correct way of binary cross entropy by setting this from logits equals true. The main difference right now is that we are really, instead of ReLU, we are using ELU. Other than that, we are doing our training. And if you look at it, you can see that in this case, there is something happening in the sense that the loss function is actually now going way below that 0.7 that we have before. And it is indeed getting very close to 0. So this is like really promising. And if you look at the accuracy scores, we are already very close to 1. So this means that in this case, we probably have a really good classifier. So let's dig into this and let's just replot that decision boundary and contour plot that we had before using this new model. So this is the new model that was just trained. And if I run this, you can see that, well, now this makes a lot more sense, right? Because it is really understanding that these two clusters belong to the same class, and everything that is here should belong to this class that is consisting of these two clusters, and everything else that are closer to this cluster and this cluster belong to the yellowish class, right? So and this is exactly what we wanted to make sure that we get a classifier that understands that we have such a decision boundary where everything here belongs to the purple class and everything outside that oval shape that we have belongs to this yellow class. Something that we have to also focus on, this is our second question here, is how to set aside validation data, right? Because with neural networks, they're very powerful and they can easily overfeed in a sense that they can memorize the data and do not perform well on new or unseen data. And in order to make sure that this doesn't happen, one of the ways is to use validation data, right? So remember, we can have training, validation, and testing data. And the way that you can really implement this is like what you had before, except the fact that you put this validation split to some number, which is less than 1. So this means that we want to put 10% of our entire data provided here for validation purposes and 90% for training. So we obviously lose some training data points, but this is a trade-off which is very important to make sure that we have unseen data points to measure the generalization performance. And therefore, you can see that now we actually get 4 numbers here. We get loss and accuracy. So this is the value of the loss function and accuracy on the training data. And then you get these things that start with VAL, which stands for validation, right? So this says that the loss function on the training data is 0.7. And if you use the same model to measure this on the validation data, is also 0.7. And this is really good, right? Because you want to make sure that these numbers are comparable, meaning that if loss function on the training data is very close to 0 and on the validation data is very far from 0, that's not a good sign because probably overfitting is happening. But in this case, you can see that we get all these numbers, which is even more difficult really to look at these numbers and understand their behaviors. But remember, inside history, we have now 4 things that we can keep track of: loss, accuracy, validation loss, and validation accuracy. And the nice thing is that if you want to plot all these things in one figure without, directly extracting these different parts, you can convert this history to a data frame, a pandas data frame, and then just say dot plot. So what this does, it understands that this has like 4 columns in that sense. So it will create a plot where now we have 4 curves inside that. The one that is the loss on the training data, the blue one, and then the green one for validation, and then the accuracy scores, right? So the loss should get close to 0. That's the ideal thing. And accuracy, since it's classification, should get closer and closer to 1, right? So you can see that in this case, the training and validation data are very much behaving the same way. And this is a really good sign that this neural network that we have is not overfitting or underfitting. So it's a right fit for the problem that we have. And we can see this behavior as a function of the number of epochs. That's why in practice, you want to make sure that you have enough or sufficient number of epochs. Depends on the problem. In these simple cases, usually 50 to 100 is a good number. But obviously, if you use a more complex model, you may need to use a larger number of epochs. The last thing we're gonna cover in this lecture is also reproducibility, right? So because when you're using gradient descent, you always need an initial solution. So obviously your final solution depends on your initial solution. And these initial solutions are chosen using some random number generation. And in order to make sure that we can reproduce our results, one nice way is to set random seeds. So random seeds, you can think of them as a way of controlling how we create random numbers, so that if we create the same, if you want to create the same random number on multiple computers or at different times, we can successfully achieve that. And one of the options, if you recall, when we look at the documentation for the dense layer, which is like the basic layer for fully connected models, is this kernel initializer, right? So this tells us how we want to initialize the kernel or that weight matrix that we have for that layer. And there are multiple ways of doing this. One of them is this method called like uniform, which is a very simple idea. It samples from a uniform distribution within some limit, which is negative limit to limit. And how we find this number is the square root of 6 over the number of input units in the weight tensor, right? Because we always have some inputs and we have some outputs going from that layer. And so this is 6 over the number of inputs, and we take the square root. These things are very much like empirical results, meaning that there's not really a theoretical reason why we should use this, but it's been shown that this works very well for many problems, and that's why it's been kind of implemented. But obviously, you can use different initializers, right? And you can see that this is a link if you want to look at different initializers that there are available in Keras. So you can see that you can have, for example, this truncated normal, this random uniform, random normal, right? So these are all the available like initializers and more that we have. But the nice thing is that if we do explicitly say what kind of initializer we want, there's also a way of setting the seed for the random number generator. And in this case, we can, for example, set that to a number. I choose 4 here. The other thing also you can do to make sure that everything in TensorFlow is done, to the degree possible the same way, is to set the random seed for the TensorFlow. And that's if you provide the same seed value. Obviously, you can use different seed values for the TensorFlow and these layers, but let's just make things simple. We just define one number, and we do the same exact thing for the output layer 2, that we use again this uniform layer or initializer, and we provide the seed that we have here. So let's see when we train what we get in the second layer, right? And look at the weights that we get, and we can train these maybe 1 or 2 times and see what happens, okay? And if you're wondering why we don't get all the information we got before, so when we do model.feed, there's this verbose option. If you set that equal to 0, you don't get a printout of all the like loss and accuracy values per epoch, right? Sometimes you may want to look at those. Sometimes you may want to just reduce the amount of things getting printed. So in this case, I want to really look at just these weights for this kind of like the output layer, right? That's like the 2 by 1. So we get 4.04, 4.34, and this is the buster. And let's run this cell one more time and see if we get the same result or very similar results or not. And it seems that we do, right? So we got exactly the same. So if you remove this seed value here or change the seed value, you'll probably end up with a different result. So for example, here I can change that to 2, and we probably get a slightly different result. This is a simple problem, so we may or we may not, but yeah, you can see that here easily, right? So before we had like 4 something, now we have these numbers. So really the input solution or the initialization technique that we use and the seed number really impacts the final solution. And that's something to keep in mind when training neural network models. I hope you found this video helpful.